This is Flappy Bird. Flappy Bird learns how to fly on its own. It needs to move to the right and fly through holes in walls. Let's see what it looks like. It looks like this. And all you can see here, the little Flappy Bird actually trained on its own. So there's no teaching it manually how to fly or flying it manually. It's just a so-called neural network, a brain which evolved over time. Now, the little Flappy Bird can only do one thing. It can either, for every step, hit jump or not hit jump. And the only thing it will see is a first-person perspective like this. And in fact, it doesn't even see that much because we only gave it 40 by 40 pixels. So this is all it can observe. And you can see it's quite smart in avoiding the walls. And it also knows its up and down velocity. And that's all it takes to train it. So what does a training session actually look like? Because we want to train the brain very fast, we don't use the real-time slow view. We use a very fast training in succession, like this. I hit train in Python in a Google library called TensorFlow. And now, when I hit play here in Unity, you can see the brain will train very fast. And for every little step, for every split seconds the bird survives in a given session, it will get a small reward. So the longer it lives, the higher the reward, and it will try to maximize this reward, whatever it takes. So it doesn't actually know anything of the world of walls or of a score that it should achieve in terms of points. It doesn't know that it's a bird, it doesn't know its own color, it doesn't know anything, but it knows the longer it survives, the more reward it gets. And based on that, it can take the action to jump in more optimized ways. We can slow this down a bit so you can see what an untrained brain looks like in the beginning. And this is at the very beginning, just going straight up to the ceiling, crashing on the first wall. So that's a new brain. But after, let's say, 1 million training steps, it can get quite good based on the visual input to survive here. Let's take a very quick look at the code behind this. So we have a bird agent which has some decorative lips and eyes, but what matters is the main cube collider, which knows when it hits a wall, and we can give it a mass in Unity, we can give it angular drag, we can give it drag, we can tell it to use or ignore gravity and so on. And we also gave it a camera, and the camera is right here in the same object, so that will cause the first person perspective, a forward facing camera. And then there's a brain included, and this is the brain, and there's a script included. And let's have a quick look at the script here. So there's common methods in every agent trained in Unity, and one of them is initialize agent, and here we just set up a bunch of stuff. We add references to the body, and to the academy, which I can show you later, and we memorize the start position so we can reset the body later. And then we have the collect observations method, and here we just add the vertical velocity. That's all we need to know in addition to the camera input. And then we have this common method agent action, and it gives us a bunch of actions. These can either be values ranging from -1 to 1, for example 0.5123, and this will be in the beginning pretty random value, but as the training progresses it will become more and more decisive. Or as we did in this example, we use so-called discrete actions instead of continuous ones, and a discrete action is an integer at the size that you define. For example, if you say size 2, you will get 0 or 1. If you say size 3, you will get one of these. So we just need 0 meaning don't jump and 1 meaning jump for every step. So we say if the vector action, the first one, the 0th one, is 1, then try to jump. We have some additional check for jump energy, which we decrease when you jumped and then increase over time again, so that you don't constantly jump. And then when you want to jump, we add some force here in the upwards direction. We use the constant 250 to make it go up. And you can see here for every step there's a mini reward of 0.001. So first step this, second step this, third step this. So the longer it survives, the higher the reward. And there's another common function called agent reset. So whenever a session is done, for example, if it hits the wall, then we will reset the body and we will also reset the environment. In this case, the environment consists of these walls here, which are moved from right to left, and once they exceed the left limit, they will jump back to the right with a new vertical position. So we create the illusion of movement here. In fact, the bird is actually static in the middle and will just move up and down. So every machine learning environment in Unity also needs an academy. This is the training facility for the agents, for the students, so that their brain can improve over time. In this case, we just tell it to observe this brain and connect it to our Python process. The academy also has a script, and in the script we simply say initialize and reset the environment. We have 10 walls and we spread them out like this. Now you could choose any different kind of observation. You don't have to choose a camera. For example, we could just remove the camera and we could actually tell it the specific positions of the walls here in terms of X, Y, and Z. We could tell it the number of walls. We could tell it to cast rays to its front and then collect observations about the objects which the rays will hit. This can actually be faster than a straightforward camera input because there's less data. So we are pruning the input to the brain, which makes it more specific and easier to evolve. And then we can also have any number of actions based on the training. We could tell the bird to move faster or slower. We could tell it to rotate around its axis. You can freely choose these input observations and the output actions as you need. And you can also have multiple birds training together. So we could have a whole bird army, and depending on your project, that can speed up the training. In the case of a camera observation, it doesn't help that much because camera means another Unity rendering, which is a bit costly, so it gets quite laggy if you add too many with their own cameras. But if, for instance, they were to observe rays instead of a camera feed, it would make sense to add maybe 20 different birds training at once. Here we have a different setup, a little maze, and there's an agent, a person in the middle, and this agent can rotate around its axis and move forward. I can now test this with keyboard input. You can see the little blue dot, the little body there, moving. And you can also see this time there will be rays cast from the center in different angles forward, and these will be the observations of this agent. And it can only see a couple of things here. It can see walls, its rays can collide with walls, it can see common balls, the green ones, and the rarer, higher reward purple balls. So those are the objects it can see. If we jump to the script, it looks like this. Observe objects in front, and here we tell it wall, ball, and rare ball are the object tags we're looking for. We give it a couple of angles to spread out, and then we perceive those. We also observe its own velocity on the maze ground and its rotational, its angular velocity. And for its actions, it can determine to go back and forward, and it can rotate left, right. So this green ball gives a reward of 0.001, and this purple rare ball gives 10 times as much, 0.01. Hitting a wall gives a small minus in this case. If we don't want that, we can also disable it. Let's see what happens if we train this brain. First, I need to go to my person agent, and instead of using the manual input player brain, I will drag and drop the learning brain here. I go to the academy, I hit control, and then I can decrease the max steps per session if I want to. There's a decision frequency of 10. And this time I'm using a special additional setting, which is called curiosity. Curiosity means to look for the unexpected. The agent is trying to get into novel situations, and this can be a quite fascinating way to speed up its brain training.
Magic, do as you will! Magic, do as you will!
So let's give this a try. We start the training session at high speed, and we hit play, and it starts with a empty, zero brain basically. But now it starts to learn, and it starts to learn very quickly. We can observe here the amount of reward it's getting. It didn't yet find any ball, so it doesn't get any reward, but as soon as it will get a reward, it will start to accumulate higher numbers here. And then it can start to learn. Almost hit a green ball here, but then it missed it again, so it keeps looking here. And I think it touched a ball here, so we can see a tiny bit of reward here. We can observe the overall learning progress in a graph by starting a process called tensor board, and the curve we are hoping for will go up and up and up because the rewards axis will get higher values over training time. And once you keep this running for, let's say, 15 minutes or something, and then you use the brain as movement again, the trained brain, you will find the agent hitting a lot of balls here. I also tried to train a variant of this one with a video screen here, and the video screen would be playing a video which was meant to sort of satisfy the curiosity of the agent. So I was hoping that it would become a couch potato and just look at the video screen playing through a visual observation. It didn't quite work out. Here's the harking video. Maybe I didn't give it enough training time. Maybe with enough training time on a visual input, it could be turned into a couch potato due to this satisfying curiosity. Here's another example. I'm on a platform on the ocean, and the platform is shrinking. And the goal of all these little cube people is to survive as long as possible. They get a reward for simply surviving. And they also get a reward when they touch another cube and that other cube will fall off. So it's kind of a last cube standing attack game. And you can see a little purplish cube in the middle, and that's the manually moving one, and the other ones are moving using their trained brains. And in this case, they're actually all using and all simultaneously training the very same brain. So all of these little attacker agents, the little cube people, they train towards the same attacker brain, but they have different reward perspectives. So if this person gains because this falls off, then the loser will get a negative reward, a punishment, and the winner will get a positive reward. So from this basic setup, depending on what your scenery and situation is, you can have emergent and kind of surprising, unpredicted behavior from the agents. In this scene I made a little truck, a little car, and each of the four wheels has its own rotation, its own torque that it manages. So it can only say forward this wheel at a certain speed or backward rotated, and the same for the other three wheels. And its goal is to get closer to a target position, and the target will switch around. Let's give this a try from the already trained brain. And there it will just move on this platform. And to help me debug the situation, I've added a green line when it's getting closer to the target and a red line when it's getting further away. It seems to be stuck for some reason right now. Maybe the brain is just not very well trained. And you can also see the perceived camera input here, because it's training based on the visuals that it's getting. If I turn off the main camera, you can see, oh, it looks like it fell on its head here. So it turned around and fell. Let's zoom in on the truck. So you just saw it fell on its head. Now you can freely design your rewards and actions and your sensory input, and based on that the behavior emerges, and it won't always be what you intuitively predicted it to be.
I need to know how Skynet gets built. Who's responsible?
For example, let's say I reward the truck by every step that it gets closer to the target, and I don't have any other rewards. So what I observed was happening before was that the agent would just drive in circles, because that would mean it would collect a lot of rewards as it was getting closer, then it would go back again to extend the session, and it would drive again towards the target but not hit it, then it would move back again. So it was kind of in an extended eternal reward loop, extending his session by never actually reaching the target but just stacking up on rewards by driving in a circle. So that's one of the unexpected results when you sort of misdesign the reward. Reversely, maybe the agent will find a new way, a novel, inventive way to solve a problem, a way that you didn't think of before, but that's actually better than you could have imagined. Here's an example where the truck is supposed to make stunts by driving across ramps and so on, and the reward that it's given here is every time a wheel is not grounded, it receives a reward. You can take a look at the code here. So whenever there's a bit of velocity, like it's not upside down on its head, then for any of its wheel that is not touching the ground, give a little reward. And I was hoping it would learn to drive, for example, just tilted sideways on two wheels. What it observes is using raycast the stuff that's in front of it. For example, it can distinguish between the side of the ramp, the ground, and the ramp surface here. After quite a bit of training, it didn't quite do any too interesting stunts, but maybe given enough training there would be more interesting stuff happening here. It seemed to just drive around quite aimlessly, but that was a nice stunt actually. One of the next things I want to try is how a curiosity-driven agent will fare in Sandbox Universe Anyland. For example, if we give the machine learning agent the actions to move forward and backward and left and right, to rotate and to look up and down and to jump and maybe to move the hand forward, will it be able to discover things like climbing up ladders or pressing buttons to get further ahead in the area? And that's all for this video. I hope you enjoyed it. If you want to try machine learning in Unity yourself, look for ML agents. And there's a Unity code repository that you can just clone to try it yourself. It's quite fun because the results are so unexpected. One of the more difficult things to do is to tune the settings. Give you a quick look at some of the settings, like trainer, batch size, beta, buffer, epsilon. But even if you ignore all these and leave it at the default values, sometimes after running it for 10, 20, 30 minutes, you get quite surprising results. And I will see you in the next video. Bye bye.